Okay, in this video we're going to take a look at some more examples of solving absolute value equations. Picking up where we left off, example 1c, we have the absolute value of x plus 1 equals negative 2. So we can set up two equations where we have x plus 1 equals negative 2, and then x plus 1 equals the opposite of that, which is positive 2. And if we solve each of these by subtracting 1, we get x equals negative 3, and we get x equals 1. Now, if we substitute negative 3 in for x, we get absolute value of negative 2, which is actually positive 2. So this one does not appear to make the original problem true. Also, when we plug in a 1 for x here, we get 1 plus 1, which is 2. The absolute value of 2 is 2, so this doesn't work either. It turns out that this one has no solution. So again, you can use the circle with a slash through it to represent no solution. But there's no value of x that when we plug it into the original problem, it'll make the left and right sides come out to equal each other. One way to know that right away, right off the bat at the start of the problem, is here we have the absolute value of something equaling a negative number. Because absolute value represents distance from 0 on a number line, absolute value can never actually equal a negative result unless there was some like negatives or whatever going on outside of the absolute value. But that's not the case here. We're just saying the absolute value of something is a negative result, and since it represents distance, it can't be negative. From a visual perspective, if we look at the graphs, notice here's our graph of our absolute value of x plus 1. Here's our graph of y equals negative 2. These graphs are never going to intersect. And as we talked about with equations and inequalities, if the graphs don't intersect for an equation, there's no solution. So no intersection point, no solution for the problem. All right, example 1, part D, we have the absolute value of negative x plus 2, and then minus 4 outside of that equals 10. So before we set this up as two separate equations, we have to get this absolute value expression by itself first. So the first thing we want to do is add 4 to both sides, and we get the absolute value of negative x plus 2 equals 14. So make sure you don't forget to get your absolute value bars by themselves first, especially if there's anything else going on outside of those. So now we can separate it into two equations. We have negative x plus 2 equals 14, and we have negative x plus 2 equals negative 14. So subtracting 2 from both sides, our first equation gives us negative x equals 12. Our second equation gives us negative x equals negative 16. Then to get x by itself, just divide both sides by negative 1, and we get x equals negative 12 or x equals 16. And we can check these algebraically. We can also check them using graphs. So here are our graphs. Can't really see it right now, but if we zoom out a little bit, here we have our x equals negative 12, and here we have x equals 16. So they do line up with the answers we got. So we got x equals negative 12 or x equals 16. All right, part E, we have absolute value of 3x minus 1 equals the absolute value of x plus 5. So yeah, it's perfectly fine for us to have two absolute value expressions equal to each other. Here, you might be wondering, well, normally I only have one absolute value expression, so I can separate it into two equations. So what do I do here? Well, the good news is if you have an absolute value on one side equal to an absolute value on another, you can pick which one you want to keep positive and which one you want to make negative. So here, I just decided to make the right-hand side the one where first up we have absolute value of, we have just 3x minus 1 equals x plus 5. We also have 3x minus 1 rather equals the opposite of the expression x plus 5, or negative the expression x plus 5. So in this case, it's pretty similar to what we've done before. Just make the right side negative inside the absolute value bars. Distributing our negative through on the second equation, we get 3x minus 1 equals negative x minus 5. So for this first one, we subtracted x from both sides. We got 2x minus 1 equals 5. For this second one, we added x to both sides and got 4x minus 1 equals negative 5. Adding 1 to both sides in each of our equations, our first one, we're going to get 2x equals 6, and our second one, we're going to get 4x equals negative 4. So then doing some division, we get x equals 3 or x equals -1. So we can check to make sure those are right by graphing these two equations and seeing if they intersect at x coordinates of 3 and -1. So let's do that. All right, so here we have an x coordinate of -1. So that's okay, that's a good answer. And then here we have an x coordinate of 3. So even though we have two absolute value expressions equal to each other, notice that the graphs can still intersect in two places. So we get these two solutions for x equals 3 or x equals -1. All right, that about does it for this video. Thanks for watching.